So we'll make him
Whoops.
go on Thursday since he's not here. So we assign him the Thursday slot.
Then how does he know that he's on Thursday slot?
Yeah, that's a good question.
He mentioned.
So,
I can tell him if we have a class with him later. So.
oh, okay, yeah, thanks. Yeah. So tell him that he has been scheduled on Thursday, and if you can't do it on Thursday, you should let me know, and we'll figure something out. Okay, so let's do the next topic.
Should students bring their own computers, or are you gonna bring your computer?
Yeah, that's a good question. Yeah, bring your own computer, because we don't have a computer here. And usually I don't bring a computer because I didn't use overhead projection that much. Probably I should use it more, I don't know. What do you think? Blackboard versus slides. So how many of you like slides? Okay, how many of you like Blackboard? Okay, so it's a trade-off. So the advantage of slides is that everything is nicely organized, and and you're less likely to forget some important point. On the other hand, if I write on the board, then I can kind of go with the flow and use the speed that seems convenient. Okay, so let's look at one aspect of software reliability. Let's talk about reliability allocation. Now, there was a question in the assignment, and where you have a serial system, and you have to replicate one, and you have to do it in a cost-efficient way. Now, that was a rather simple example, but actually it's a trivial example of a rather general problem of reliability allocation. And it's a famous problem in reliability engineering, not just in software, but in other fields, wherever they want to use reliability. So the idea is that you want to make a system reliable. You have a system which is composed of components, and you can use some redundancy or something to make those components more reliable. And the classical problem is that you are allowed redundancy, so you can replicate something. And so usually they talk about a problem where you replicate some component, and how many copies of that component you would need, and which component you would replicate. And so here, let me give you kind of a brief summary of one part of the problem. So traditionally, this is a problem that people have worked on for several, I think 3 or 4 decades. And typically just the objective is to what components to replicate. And now there is a similar problem in software reliability. Now in software reliability, you can replicate components, as we were talking about inversion programming. And however, there is a general problem in software reliability. You have a component, and if you test it and remove bugs from it, it becomes more reliable. So let us say you have a software project with a number of components, and these components are of different sizes and probably with different defect densities. So what is the optimal way to allocate your testing resources in order to achieve the highest reliability. So let's consider this question. And the reason I got into this a few years ago, so somebody who was compiling an encyclopedia, he contacted me and asked me if I could contribute an article to optimal reliability allocation. So I thought about it, and I said, okay, I'll do it. So I scanned the literature, I found all the papers on reliability allocation, and specifically, since my field has been more software reliability, so I looked at software reliability applications. And I did some analysis, and here's the analysis, the part of the analysis that I did. So let's say we have a number of components. So we have modules, and the modules are, let us say we have, let's see how many do we have. We have n. So we have n modules. And each of the module has its own defect density and hence its own parameters. And let us assume that from a module I, you have the failure intensity. Let us assume that it is given by the exponential model. So we say lambdas of I, which is a function of the testing time. So this is the testing time. Testing time, let us say it has been tested for t sub I time. And that is equal to some lambda 0. And let me put I there to indicate that this is referring to module I. E raised to minus beta 1. And let me add a subscript I there, because we are referring to module I, di. So, the failure intensity of a module depends on how much it has been tested, right? So this is the exponential model. Remember this? We talked about it a few days ago. And this is, now, one key problem in the reliability allocation problem is to find a relationship between cost and reliability. So what is the cost and reliability relationship? And this is referred to as the cost function. So this is something that the reliability theorists have struggled to come up with a cost function. So I looked at some papers, and some of them they come up with some mathematical expressions, and they consider that this is a reasonable choice for a cost function. Now actually in software reliability engineering, cost function actually arises naturally. So once you have this, and it is, the exponential model is a reasonable model. It's not perfect, but it's a reasonable model. This gives you a way to connect cost and reliability. So if you assume that the cost is basically determined by the amount of time you have spent on testing, then here's the cost function. D, which is the testing time, as a function of lambda, which is a reliability attribute. So using this, lambda 0, incidentally, is the failure intensity at time t equal to 0. So here's the cost function. So this is the cost in terms of testing time. And notice if you look, this has the right properties for a cost function. So basically, assumption is something more reliable costs more, which is usually true, right? Occasionally, you may be able to find some inefficiency in pricing. Sometimes you can buy something that is more reliable and may even cost less. For example, if you have been reading that how many of you read Consumer Reports magazine? So if there is some inefficiency in the market, but if the market is efficient, high reliability stuff will usually cost you more. So this satisfies that property, and also satisfies the property that as your reliability goes higher and higher, it becomes more and more expensive to further achieve higher reliability, because you are in the region where defects are much harder to find. So at higher end, it becomes harder to improve reliability. Okay, so here our, so let us say that block I is under execution. Module I is under execution. For time f sub I. Under execution for fraction of the time f sub I, such that summation of x I equal to 1 to, did I say n? Would be 1. Then we can set up our optimization problem. How many of you have come across optimization problems? So it's a very common thing. So once you have set up the optimization problem, you have done half of the work, because that's the part that sometimes takes some skill. So here's the optimization problem, which I can write here. Why don't I write here? So here's the optimization problem. And this is one way to write it: minimize total cost. And let us say the cost is given by C, which is equal to the summation of. Now you will notice that I'm considering only the testing cost, and I'm not considering the development cost. Does that look reasonable? What do you think? I'm not considering the development cost. So that is actually reasonable for two reasons. Testing cost can be, in a large software project, could be something like 60–70% of the cost. Secondly, you can assume that the development cost is the same. So once you have developed, then the question is how much you should test. So since the development cost is the same, and so it's the same for all scenarios, so this is a common thing, so that's it's the same value for all options, so you don't have to consider it. You only have to compare the option which varies. So that's a reasonable thing to assume, that you want to minimize the total testing cost, and you want to achieve